Welcome to Symposium 3. The theme of this session is Progressive Textile. The presentations will include Sustainable Textile Technologies, Textile Engineering, Technical Textiles and Composites, Textiles of the Future.
Our off-grid PV solar system. It comprises of the PV modules or module, and then it's connected to a charge controller, which is basically a switch. A charge controller interconnects the battery, the inverter, and the loads, as you can see that simple diagram. And that is how the energy flows from the sun to the module, the charge controller. Part of the energy goes to the battery for storage, and when needed, it is released through the battery, through the charge controller to the inverter, and if it is a AC load, and direct from the charge controller if it is DC load. So the aim here of this presentation is to discuss and compare two photovoltaic solar sizing systems, the charging current method and the energy management method. I'm also discussing how to provide a simple, accessible, and cheap photovoltaic sizing methods, mainly for solar home systems. And here we are talking about small systems for rural application. So why is it important? Because most commercial sizing softwares are expensive and complicated for solar home sizing design. It provides simple and cheap methods for sizing of solar systems. This, when applied, will tend to develop some confidence and the professionalism in the solar engineer when they're installing the solar. And definitely, when the client is satisfied, it will enhance the promotion of solar intake in the country. This will also help in acceleration of goal number 7, the World Sustainable Goal, which is energy access to all, which is affordable and reliable, and of course, modern energy, especially the rural communities in this country. So we go to the main methodology, and the first step, of course, is called a site visit of the installation, where you install the system. This gives you some one-on-one information on exactly where the system will be installed, and be able to discuss with the client what really the client needs to do on his or her part so that the installation can be successful. Here you ask the client the future needs of the system, the current needs of the system, whether they have plans for future installation, and you also assess where the system will be installed. If there's need for clearing the bushes around there or changing a few things here, then you inform the client what to do. So the site visit is usually very important. Once the site visit is done, then you determine the solar resource in the particular area. And this one you can get from resource maps on the internet or the nearest meteorological station. The third step is now you compute the daily energy demand of the client. This is after now discussing with the client. Once we discuss with the client on the needs, what devices they want to power and what they are planning in the future in terms of buying other clients or adding more rooms in the particular installation, or there's a building where the system is installed. So you can make a simple table here with about 7 columns, where the room is where the device is located, column 2 where the appliances are, the system voltage, then column 4 is the appliance rating according to the manufacturer, how many hours it will be on per day roughly, and the total power that is consumed, and then we have the daily energy demand in hours. The daily energy demand in hours is what we want. So you multiply the rating of the system of the device times the number of devices of that particular rating times the number of hours they will be on per day. Then you sum up that to get the estimate of the total daily energy demand of the client. Of course, we add a percentage above 25% for estimates to that value, so you tend to have a higher figure. So the next step now is to determine the number of solar modules in this charging current method, the number of modules that is needed. And once you have determined the system voltage, then the next thing you need to determine the this demand, daily energy demand in watt hours to get the charging current of the system. Once you do that, you go to the market and check the types and sizes of this module of panels that are available, and you get a right combination of the panels that will give you that charging current to the batteries. So you may get one panel that will give the charge current, or a number of them, when combined and connected, either in series or in parallel, will give you that particular charging current. So you choose appropriately depending on what is in the market. Then we get the number of modules in a parallel in a string. We get this by you divide by the charging current by the maximum current of one panel. We get also the maximum. We divide the system voltage by about 0.8 of the maximum power, so that we get the number of modules per string. The modules can be in a string, and then the strings are connected in a parallel. That's exactly what we mean here. So when you combine step 4.5 and 4.4, then you get the total number of modules in the system. That is, how many are in series and how many strings are there that have those number of panels or modules in series. You get the total number of panels you need. So, ladies and gentlemen, you got step number 5, and now we are through the panel. So we got the battery bank, and the battery bank now is, we get the daily energy demand, which you calculated in ampere hours. We multiply that by the days autonomy, which are the days now which the client wishes to have power when there's low sunshine or there's a lot of cloud cover. And this has a direct implication on the number of batteries and the battery bank size that will be available to the client. So this means money now. So one has to be careful with this. The more days you include, then the more batteries you need, and the higher will be the cost. So we divide this by the depth of the discharge. That is, we call it a DOD. Go to the market, choose the right sizes of the batteries that you need. And when you want to determine the number of batteries in number of parallel strings of the battery, you divide the battery bank capacity you have obtained up there with the rating of one battery in ampere hours. Then we also need to know how many strings are really connected. Okay, how many batteries are connected in series in one string? And this is obtained using step 5.4 and 5.5. We divide the system voltage by the voltage of one single battery to get the number in each string. Then we multiply those two, 5.3 and 5.4, to get the total number of batteries you need, so that you now, your system needs this number of batteries. The charge controller is a watchman to the battery. It prevents overcharging and discharging and over-discharging of the battery. And so it's a very necessary device. Otherwise, the batteries will just die away so fast if they are either over-discharged or overcharged. It reduces their lifespan. So to get this, you get the IC of one module and multiply by the number of parallel streams of modules connected. The inverter is a reflection of the total energy demand for the client, and we add all the power of all the devices that will be connected to the solar system. And that gives you roughly the estimated size of the inverter. You go to the market and get the inverter that has slightly higher rating than what we have obtained here. So cable sizing have been done professionally so that we can minimize voltage drop and losses along the way. We keep the distance as short as possible. We try to use as thick cables as practically possible. Now, that deals with the charging current method. Why do we call it current charging method? Because the charging current determines the other values of the other balance of system devices. Now, let's consider the energy output method. And the energy output method, we still have your daily energy demand at the end where you see the loads, and then you calculate backwards. And the question you ask yourself is, if you have to give an output equivalent to the daily energy demand, assuming that the inverter has an efficiency of 80%, how much energy will you put to the inverter so that you can extract an energy from the inverter equivalent to the daily energy demand that will go to the load? So you compute that, factoring in the inverter is about 85%. This is just an estimate. This is just an assumption. Most inverters have an efficiency of 97, 98, so I just took 85. So whatever figure it is, you apply it here and see. Then you ask yourself, okay, for the inverter to be able to get that energy I've calculated now, how much energy do you need from the battery so that you can get that? That means the output of the battery is the same as the input at the inverter. So you calculate that, keeping in mind that you assume the batteries are giving about 80% of the energy that they have. And you work backwards all the way to the solar panels, asking yourself the same questions. The charge controller is basically a switch, so it consumes basically no power. It's just a transit point or a control device for the entire system. So what is here now in this slide is exactly what I've just described. And we don't need to go word after word because I've just described in details what is supposed to be done. You work backwards, factor in the efficiency of each of the devices, and then you'll be able to get the energy that needs to be released by the previous device or balance of system so that you can get the energy you want out of the other device. So once you do that, you can get the number of modules, the parallel strings. You divide them by the total system once by the rating of one module. And you can determine the number of modules you connect in a series per string by dividing the system voltage by the nominal voltage of one module. And then you multiply steps 5 and 6 to get the total number of modules that you need. The sizing of the charge controller is done just the same way as the charge current method, that you get the ISC, that is short circuit current on one module, multiplied by 1.25. 25% is just a margin, an error margin, or inefficiency margin. The battery bank capacity is determined by the battery output, and you divide by the DOD, or daily depth of discharge, in a percentage. And when you do that, you divide the resulting value by the system voltage, and that gives you the battery capacity in ampere hours. So you go to the market and choose the right battery so that you can be able to determine, you can get a series of smaller batteries, you connect them, or one battery that serves the particular purpose, depending on your computation and how you have been able to do it. So the total number of batteries is also obtained using the same method, that you get the number of strings and you get the number of batteries in each string, then you multiply the two to get the total number of batteries in the system, or what you call the battery bank. All right, so these two methods were applied to a conventional assumed system, and we assume here the client has a delegated demand of about 904 watt-hours, while all the total appliances actually consume about 168 watts, and the installation that places about 5.5 kilowatt hours per meter squared, roughly, probably around Nairobi, is around this, depending on exactly where you are. So we applied this method to each of the methods. We applied this symbol here, or problem, to each of the methods, and this is what we estimated. So the number of modules using the charging current method is about 4 panels, each of about 8 watts. We got batteries, about 7 batteries of 200 ampere hours. Why are they many? Because we took in consideration 3 days of autonomy. And then we have a charge controller of about 26 amperes. So in the market, you may not find exactly 26, so you get to the next higher, which is 30 amperes, 12 or 21 volts, depends. It can choose. Most of them are digital. They can choose whether you have connect 24 or 12 volts. And then the inverter is about 200 because we got about 168 for that. So about, because all the power added is 168, so we can go to 200 watts. The energy output method gave us 4 panels or so, about 7 batteries, the same charge controller, and also the same size of the inverter. So the two methods actually have provided the same values of the results. They are actually basically the same. The only difference is that the charge current method needs you to have an idea of the technical specifications of the panel you want to install, because you'll use that in computing the sizes of the other devices. So you need to have information on the panel you want. And since there are 4 panels, then you can connect them in parallel with the 2 of them connected in series. So we see here the total charge current is 1695. You divide by 4.27. That means that you can have the 4 panels, you connect all of them in parallel. Or you can have 2 panels, each with a charge current of 8.47, and it will still do. So it depends on what is available in the market. So it looks like it may be easier to deal with the power rating rather than current, because most of the people who deal with the modules or panels actually tend to relate or identify them by the rating of the panel. And the second method, the energy output method, actually deals with that, or gives you the output of all the panels once you compute it. So I need to mention that the desk autonomy increases the bank capacity, and it is also not advisable professionally to mix batteries that are whole or different companies or different ratings, because you waste batteries in the process. It's not recommended. Don't connect more than 4 strings. And for the charge controller, it can choose the system voltage that you are connected to it. Most of them are intelligent these days. So both sensing methods are quite straightforward. They can easily be applied in an Excel sheet. They provide simple, easily accessible, and useful tools, especially for the local person. And as I said, the energy output method appeals more to the installer because you talk about the size of the panels. And in conclusion, we have considered the 2 methods of sizing a solar home system, and both methods can easily be adapted step by step, as I have presented in detail, so that one can even copy it and try to apply it, and it works. So both methods actually converge at the same values once applied to a problem, and therefore it can be applied to most of the PV solar designers and engineers for accessibility. So we need to know that the energy output method appeals more because of the power issue, that is the rating of the panels in terms of power. And when this is done professionally, then it will boost the optical power and make many people in the rural areas have access to electricity, which tends to be elusive in most cases. Ladies and gentlemen, I will not conclude until I thank the National Science Program Sweden, who is our long-term partner, and we continue to partner with them, the organizers of this conference, and you for your attention. Thank you.
Yeah, thank you. Thank you so much, Dr. Waita. It could not come better than the way you put it. It's a topical issue. So I know there are a lot of issues to come up, and I can see already, Dr. Nzila, your hand is up. I would want to say, Dr. Waita expects quite a lot of responses, starting with Dr. Nzila.
I'm ready, sir.
Thank you very much, Professor Gitaiga, for the opportunity to ask, to interact with Dr. Waita on this wonderful presentation. Dr. Waita, I noticed 2 issues in your presentation. First, you quote the electricity penetration rate in the country by 2018 to have been less than around 76% or something like that. I would like you to clarify the source of the data, because the information we have is the penetration rate in the country is more than, not less than, the figure that you're quoting. That's the first one. Then the second one, I notice in your computation, you make use of a solar PV efficiency of around 80%. However, the highest efficiency we know in the market for PV is around 42%. So I'd like to know which panels are those which you use with the 80% efficiency. Thank you.
Okay, Chair, with your permission, I can respond to that.
Yes, please, the floor is yours.
Yes, thank you, thank you. Penetration, yes, about the penetration, I'm aware. In the government report, there's a percentage of about 73.3%, if that is what you meant, I'm aware of that. And I additionally took less than 70 because another report gives 63.3. I know the last mile connectivity has really tried to push this connectivity to another level. And what I'm saying is that these are just purely estimates, and the two figures should be 75% and less maybe, because I remember 73.3. And I was trying to get a balance between the 63.3 I read and 73.3 that I saw both the reports. in the government circles. So that's a figure we can apply. We can confirm further, please. Thank you. The second one is about the PV efficiency of 80%. And when we talk of the efficiency of the PV efficiency, we are talking about how much of the power of the module in the real field can be converted into useful power. When you talk of 42%, probably you're addressing to the lab solar cell. Here we are talking about the module. How does it perform the entire module in the field? It doesn't give the 100%, but it can give to about 80-85% of its performance. That is my experience. Thank you.
Okay, thank you, Dr. Waita, for that. I think the interaction with Dr. Nzila can still continue in the background, but in the meantime, Dr. Stephen Talai, I see your hand is up. Please fire your question.
Thank you, Professor Hidaika, the chairman, and thank you, Professor Waita, for your nice presentation. My query in these particular two methods of approach in sizing is that it does not take care of shading. It assumes a clear day whereby you don't have clouds. But most places in Kenya, we have clouds. So how can these particular two methods take care of the clouds so that now we can get an accurate estimation? Otherwise, it will suffer from a lot of inaccuracies. Thank you.
All right, thank you for your question. And I would say that probably the issue you're talking about is taken care of in this aspect, that although most of the sizing is done, we usually use the design month as a worst scenario in the year. For example, in Kenya, we tend to use the month of June and July, where we have the highest cloud cover as the design month. And that means any other month can only have more sunshine and not less. That is one strategy we use. We use the lowest cloud cover, the highest cloud cover as the design month. Secondly, we try to factor in that by using what I call the days of autonomy. That is, how many days would the client like to have the system running and providing power when there is low or no sunshine at all? That's how we try to factor that in. Of course, in solar systems, as we install solar systems, as you get experience, you realize there's a lot of balancing because few clients will have the amount of money that you exactly need to install a system that will meet their entire needs. The needs will always be higher than the amount of money they are willing to spend. So we also advise them on how they can juggle and balance the use in the process. And that's what we call user training now, which we conduct after the installation. I hope I've answered you, sir.
Yeah, thank you, Prof. Yeah, you have answered. Thank you. Thank you for that.
Yeah, thank you. Thank you, Doctor. Thank you. Thank you so much, Dr. Waita. I know your topic is very topical, and therefore we can flood you with all type of questions. I want to give the last person. This is Mike Tebia Tekelwa, I suppose from Rwanda, to ask his question, and then I will protect you by saying other questions can be put to you directly or informally, not in the open session. Although I would wish that as you answer the questions of Mike, you tell us the cost of the two systems that you computed for us. Okay. So, Mike, you can ask your questions.
Can you guys hear me?
Yes, we can hear you.
Yeah, my name is Mike Kibitekram. Actually, I'm from Uganda, not Rwanda. I'm from Kampala. So my question is will be short and it will be precise. I think I'll get a precise answer. I wanted to understand and to know how long is this system designed to run? Like, because we know the time is going to affect the final cost of the power you're going to generate. So what time did you like use to simulate everything? How long is it gonna last? 20 years? I mean, 15 years? I don't know.
All right, thank you. Thank you so much, Mike, for your question. And I would like to answer it this way, that the system has a number of components. And each of the number of components may have a different lifespan. But generally, a well-installed system, generally now on average, is supposed to take several years, maybe 15 to 20 years, I should say. But it doesn't mean that the system will be dead. No, it will still operate, but it will not be at optimum. Let me say modules have a guarantee of performance between 20 to 25 years. That's the guarantee we are given by the manufacturers, and most of them actually go through that period. But the panel now performance has reduced slightly to has gone down because it decelerates, of course, in terms of production and power production as years go by, depreciation that is. For the batteries, now the time span or longer to be there depends on one, maintenance of the battery. And maintenance means that is the battery being taken care of well? Are you wiping the terminals? Are you getting it fully charged and not keeping it fully discharged for long periods of time? So this is a factor of maintenance and the use, and may vary between 2 years all the way to about 7 years. It also depends on the quality of the battery you have bought. There are several qualities in the market.
Can I interrupt a little?
Yes.
Like my question is, did you account for this into your final cost per kilowatt? All these points you've been mentioning, did you account for them?
For the time the system is supposed to be working?
Yeah, for the time between all these peripherals are going to be working and the final price, the final cost per kilowatt, did you account that there's a possibility for failure and it should be at this time? So if we require maintenance, we are going to incur this much, and that's why our cost is this right now. Did you account for this?
Yes, I computed, although I didn't put in the report, but we computed it elsewhere. And usually when we are doing the installation of solar systems, we normally give a guarantee of 1 year for the system to be working optimally. And to give guarantee of equipment that we have not manufactured ourselves. So we also rely on the manufacturers who have supplied us on the guarantee they have given us. Ours is on the installation, the professional aspect of installation, 1 year. If it fails, katikati, then we come and replace at our own cost. Thank you, Mike.
Thank you very much. Thank you very much.
Okay. Hello.
Hello.
Yes, I think I would want to say that I'm expecting that questions will keep on flowing, but for this purpose, because of time, I see we are running short of time. So I would prefer that then the rest of the members can channel their questions to Dr. Waita through the channels which I think he included in his presentation. So that at this time, I would want to ask, did Mr. Joseph Uraku show up during the presentation? Our second presenter, has he shown up? Caro, I'm asking whether the second presenter has shown up. Okay, so can I take this opportunity then to say for the two presenters that we had, it's unfortunate we can't clap for you. We are far apart, but we want to thank you profusely for doing that excellent presentation, and for that we are thankful. Now, the fact that we don't have our last presenter, I would want to say we can keep the system a bit open, maybe for another 5 minutes if there are further questions, and then in exactly 5 minutes we close. If you have any questions for the first presenter or the last presenter or for Dr. Waita, who has just completed, I'm giving a chance for 2 or 3 questions, and then after that we close. If there is any further questions in that case.
There was Yvonne. Yvonne, you can ask your question if you're around.
Well, if Yvonne is not here, anybody else can ask. Well, there being no other questions, as I can see, I would like to request our, oh, I see there is a hand which, oh my.
Am I allowed to ask again?
No, unless there is no other person, because
Okay.
we should give everybody an opportunity.
Okay, sure, thank you.
Yes, if there is no other person. Okay, Mike.
Yes.
Mike,
yes.
have it and make it short.
It's okay. You can continue because it might get long and long.
I'm saying you can ask your question.
Okay. Is the presenter still on? Yeah. I wanted to inquire also still about cost, because actually I happen to be having many questions about this, because I know when we are calculating the cost per kilowatt, the final cost per kilowatt from a system like this, we need to consider many things. For example, even the appreciation and depreciation of the fees, for example, the currency and everything. So I'm wondering, because you gave us the final figures of merits, but I'm wondering if they are really legit, we can really trust them. Did you consider like the appreciation and depreciation of the systems, looking at the currency in future, and then coming up with a final cost per kilowatt? Because in most cases, we design systems like this, we put them up, but to find out later that it's going to be hard on the consumers.
Mike,
point. Yes,
Mike, if I can intervene. In the presentation by Dr. Waita, I didn't see him providing any costs. He only provided the systems, and he only provided how it's supposed to be done. But it's me who asked him whether he could indicate what is the cost of the two systems. So when you ask more about cost, I don't remember him discussing costs. But Dr. Waita, you are here.
Yes, thank you so much, Chair. I think you are right. Definitely, you are right. I didn't discuss about the financial analysis and implications, and I know what the mic is alluding to, and there's a whole process of doing that. Performance of our PV system, where you go to the performance ratio and payback time and all that details of that. That can be done separately, and I always do it, especially for big systems, that is, not for very small systems. But for small systems, one can also do it. When you break even, you have put this money, when you break even, that can be done also. But that was not my focus in our presentation. Mine was just a simple way of how we can be able to do sizing. Coming to your question, Chair, I think the systems that I've done around this range have costed between 200 and 250,000 Kenyan shillings. Everything included.
Okay, thank you so much. Can you, Dr. Waita?
Yes, sir.
Kindly share your contacts with Mike so that this discussion can continue after we have closed the session.
Yes, thank you. That would be good. Thank you very much.
Share the contact with you so that you can continue the discussion, please.
Yeah, thank you so much. Mike is a guy we can work together. Asante sana, Chair.
Thank you very much.
Okay, so with that, ladies and gentlemen, I want to thank all the participants. I want to thank the presenters for a job well done. And I want to say thank you so much. The next time when COVID is gone, we shall do this one face to face. Thank you and enjoy your afternoon, evening, or night. Thank you. Our session is over. You can now go to the poster session and see what is being presented. Thank you. Thank you so much.
Thank you, Chair.
Karibu, Prof.
Asante. Are you here?
Yes, I am.
You arrived?
Yes, I'm
We have
back. I'm
given
back.
a ceremony. It's okay.
I'm back. I'm back.
Okay, okay. We'll see you.
Thank you. Thank you so much.
Thank you.
Okay. Thank you, everybody.
Welcome to Symposium 3. The theme of this session is progressive textile. The presentations will include sustainable textile technologies, textile engineering, technical textiles and composites, textiles of the future. Welcome to Symposium 3. The theme of this session is progressive textile. The presentations will include sustainable textile technologies, textile engineering, technical textiles and composites, textiles of the future. Welcome to Symposium 3. The theme of this session is progressive textile. The presentations will include sustainable textile technologies, textile engineering, technical textiles and composites, textiles of the future.